Now I'd like to talk about a method for testing whether you've been overfitting. There's lots of ways to do this method called cross-validation. I'm just going to give you the simplest possible way of doing this, but actually it's enormously powerful. And I don't mean that in the technical sense of this concept power we learned, but I mean that this is an extremely useful technique for making sure that the model you choose is not just describing only the sample that you have, but rather might be generalizable to a larger population. Here's the idea. You randomly divide the rows of your data set into 2 or more parts. Let's say 2 parts. It could be or more. Let's call them 2 or more subsets. Okay. Let's call the subsets, call the 2 subsets train and test. We use the training data to select the model. In other words, you take your data, and before you do anything to it, you randomly divide it into 2 parts, and you reserve half of it, or at least some percentage of it, for later. Why would you do that? Why would you not look at all the data? Well, let's see. So you have this subset of the data called train. When you explore your data, when you visualize your data, when you run hypothesis tests on your data, and when you try to select a regression model to fit your data, you use the subset called train, and you do not open the part called test. In fact, if you can, give it to somebody else, to your collaborator, and don't let them give it back to you. So you take that data, maybe here's train, I'm going to draw the train data set, the subset of dots that I decided to include in train, and use that to choose your line, fit some line, okay, if we're talking about regression. And you come up with some model, right? So perhaps maybe my model says that the mean of y given x is, I don't know, 3 plus 7 times x. Right? We're making that up, but that could be the intercept and slope that you estimate from the data set, but you're really only looking at a subset of the data. You're looking at the trained data set. Okay. So if we weren't doing cross-validation, after fitting the model, you'd just be done. You say, hey, I did my best to choose a good model, right? I used my knowledge of the context. I was thoughtful about choosing linear regression at all, as opposed to something else like a regression tree. I used visualization to help me understand what model might fit well. I looked at the residual versus fitted value plots to help me check my assumptions. I considered whether I needed to log or transform in some way. I thought about measures of model fit, right? So maybe I looked at the AIC or the BIC or the R-squared or the adjusted R-squared. I did all those things, and this is the model I landed on. Again, if we were not doing cross-validation, you'd be done at this point. You'd say, here's my model, right? This is the model we should use to make predictions for the future, right? And 7 is the slope that we should use to interpret the relationship between x and the mean of y. However, we are doing cross-validation, so we have some leftover data called test. Here's what we're going to do. We're going to use the model chosen based on train. In other words, this model right here, right? To make predictions for the rows in the other subset of your data. Right? So here's x and here's y. And you look at all the x values. So in the test data, maybe I have somebody whose x is, I don't know, there's 0, and somebody else whose x is 2, somebody else whose x is 3, and somebody else whose x is 10, right? And I stick those values, which are the x values from the test data set, into this model. So if I'm thinking about 0, okay, 3 plus 7 times 0, hey, that's 3, right? And I've got a number. Stick the 2 in next, because maybe that's the x value for the second row of test. Okay, 3 plus 7 times 2, 7 times 2 is 14, that's 17, okay? Maybe it looks like this, whatever it is. I'm gonna get a bunch of predictions, right? I'm gonna get a bunch of predictions. And what I'm then gonna do is I'm gonna compare the predictions from the chosen model to the actual outcomes in the test data set. In other words, suppose we're trying to predict people's incomes, and there's, suppose, I don't know, 2,000 people in your data set. So you might take 1,000 of them and work really hard to take those 1,000 people and choose a model that describes the relationship between the background variables. Maybe it's things like job and education level and gender, right? And figure out what model you can use such that you plug in job and education and gender and get back out a prediction of income. And you do all that based on just the 1,000 data points that are the 1,000 people who are in the train subset. But if you're worried that you're overfitting, which you should be, because you never know if you are at that stage, then you can take the 1,000 people who you saved in your test data set and take their jobs and their education levels and their genders and plug them into this model that you fit using train and get a predicted income for each person in test. And then you can compare the predicted incomes from test to the actual incomes from test. And what you're looking for is to see whether you're close. Now, I'm not going to give you any particular kind of rule about how close it needs to be, right? And we could talk about this concept for a whole week if we wanted to. But the idea is that if the predictions from the trained model used on the test data are pretty close to the actual test outcome values, then you did a good job. You didn't overfit because the model that you selected based on train actually did generalize and still work on the test data. However, if you're overfitting, right, then even though the model you chose may look great on the train data, maybe it has really small residuals in the train data, if you're overfitting, then when you try to use that same model to make predictions for tests, it's not going to work, right? Like suppose in the train data, there's one huge outlier, like somebody who is unemployed but makes $2 billion a year, right? And suppose that person's in your train data. Well, maybe you have really small residuals in your train model because you now predict that when somebody's unemployed, they're going to make $2 billion a year. Well, that's because of an outlier. That is not generalizable, right? So when you look at if you take everybody in the test data who's unemployed and predict that they're going to make $2 billion a year, you're going to be wrong, and you're going to have giant residuals. And if you have giant residuals, when you compare the actual outcomes in the test data to the outcomes in the test data that you'd predict using the train model, that tells you that the train model has overfit. So this is an enormously useful idea of saving data for later, and there's more versions of it. I said you could split the data into 2 or more subsets. So the other versions of cross-validation involve having more than 2 subsets. For example, there's something called k-fold cross-validation. So suppose k is equal to 10. You could split your data set into 10 parts and take turns using each 10th of the data to fit a model and check it on the other 9 parts. That's essentially the idea, right? But there's a lot of other extensions of it, or something simple that you could do. Suppose you wanted to have kind of a final check. You could split your data into 3 parts. They don't have to be equal proportions of the rows in your data set. And you could use one for your initial model and then check that model against your maybe intermediate data set. And if you don't like the fit, then maybe go back a couple times, go back and forth between your initial data set and your checking data set until you think you've done a good job and you're not overfitting. And then only at that point, go check it on your final data set to see if you've really done a good job. I'm going to just tell you a quick story about an example of a contest that went like this, which was the Netflix contest. You guys know what Netflix is, but a number of years ago, it was probably right around like, I don't know, 2008 or so, Netflix was trying to find a way to improve its prediction algorithms. In other words, when you were looking for a movie to watch, Netflix wanted to do a better job predicting what movies you'd like based on past movies that you'd rated, either liking or not liking. What they could have done is hired, a consulting firm to do that an analysis for, you know, some amount of money. What they did instead is they offered a $1 million prize to any person or group who could come up with a good model. And this was the first of what is now very popular crowdsourcing model fitting. In fact, if you go to a website called Kaggle.com, you'll see there's more of these. There's always contests being posted where people are offering money or sometimes job interviews based on, you know, whoever out there in the world can do the best job with their data set. But Netflix and the Netflix contest was basically the first to do this crowdsourced modeling contest of this size. But here's what they did. They released one data set, okay? And that is the data set that people use to try to come up with a good model. Then they posted a website that used another data set. Let me write that correctly. For checking. So if you're trying to win the Netflix contest, you work on the data set that was released. Then if you think you've done a good job, you type into the website essentially what your model is. You can submit your code for what your model is, and without showing you the second data set, the website uses your model to make predictions for the second data set, and it posts how well you did, right? In other words, whether you did a good job making predictions for the second data set. And they had a leaderboard where they were showing how well different teams were doing. Of course, in order to win the $1 million prize, you had to, you know, your predictions had to be a certain amount good, right? They had to be, you had to make the residuals small enough to win the $1 million. But the problem is that if they're going to post this leaderboard, think about what you could do, right? You can repeatedly submit different possible models to the website and see which possible models make you increase or decrease on that leaderboard, right? So you could say, hey, I tried this model, but it looked like I was overfitting a little. So I tried this other model, which I changed in some, you know, way that wasn't that well motivated. And I noticed I got a little better on the second data set. In other words, you can cheat if this is it, right? You could just try every possible model submitted to the website until one of them happened to come up with small residuals for the second data set. So here's what they actually did. They had a third data set for the prize. So what they did is they had this leaderboard posted, and people tried for, I think, over a year to submit different models until one of the models finally looked like it did well enough. And I think it might have even been a tie. It might have been two teams that actually did finally well enough. It seemed like they might have a chance at winning. Only at that point, then Netflix took those models and applied them to the secret third hidden data set to see, and the winner was determined based on what model had the best predictions for this third hidden data set. Not the model they had released, not the one that the website was using to produce a leaderboard, but a third one, because that way the winning model was definitely going to be one that reliably for any data set in a generalizable way could use the available background variables to make predictions. So that's the Netflix contest. And again, it was the first of what is now a pretty common idea of crowdsourcing models. The last thing I want to say about this idea is just to give you a sense of how a good model fit might be measured in this sort of contest. So recall how we measure residual variance. So the residual variance is the sum of squared residuals divided by the sample size minus the total number of betas, right? Okay. So the only thing about this quantity, we could use this, we're trying to come up with small residuals, but if our goal is prediction and prediction only, let me spell prediction correctly, and we are cross-validating, then we only have to worry about the sum of squared residuals. We don't have to use a measure of model fit that takes into account P. So let's big picture, think about that for a second. When we started talking about model selection, we said that it's a trade-off between how small the residuals are, and how many parameters you needed to achieve that, right? Now, why do we care about how many parameters you need to achieve a certain model fit? Well, the reason I've been giving you is overfitting, right? You don't want to have a model that only describes the sample and doesn't describe a more general population that you might want to use to make, that you might want to make predictions on in the future. But if we're going to be cross-validating, that's going to be a check for overfitting. So maybe I don't care if I have too many predictors, I'm going to find out when I cross-validate. There's another reason to want to incorporate P when we're measuring how good our model is, and that's for interpretability, right? So if I give you a model that relates income to a bunch of predictors like job and education and gender, I'm going to be able to understand the model results better if I have fewer predictors. In other words, if you give me a model with estimated coefficients for how job categories and education categories and gender categories relate to income, if you have 500 different job categories, it's going to be really hard for me to understand what this model is actually telling me about the relationship between job and income. But if you have reduced job to only 3 categories, then I might actually be able to, just by looking at the model, learn something from it. But that's not what we're saying here. If our goal is only making predictions, not trying to interpret the model, then I don't care how many parameters you have. Use however many you need to make good predictions. More predictors is not a bad thing if your goal is prediction as opposed to interpreting the model. And the other reason I might worry about having too many parameters is overfitting, but if I'm cross-validating, I'm already taking care of that. So all that is to say that usually when you're doing a prediction contest, like the one I just described, instead of using sigma hat squared as your measure of which model is good, in other words, the measure that determines that leaderboard of the Netflix contest, you use something called root mean square error. Yeah, let me spell it correctly. It's RMSE, root mean square error. Which is almost the same thing as sigma hat squared. RMSE is equal to the sum of squared residuals divided by n, instead of n minus quantity p plus 1, and then you take the square root afterward. So note that like this quantity is almost exactly the same as this quantity. The difference is whether I subtract the p plus 1 from the denominator, and also whether I take the square root. The square root, that's a preference. It's not a big deal whether you take the square root or not, as long as you know whether you took a square root or not. But the main thing is that this root mean square error, the usual measure for a prediction contest, does not have a p in it. And I'm going to repeat why one more time, because if all you're doing is making predictions, then a more complicated model is not a problem. Like Netflix does not care if it took 100 variables as opposed to 3 to make a good prediction. And the whole point of cross-validation is to avoid overfitting, so I don't have to worry about using P to reduce my, or to change my measure of the residuals. The only purpose of root mean square error is to measure the residuals, and so if you're trying to compare a bunch of models based on their residuals alone, not on the number of parameters, root mean square error is the way to go. And this is how you calculate it. Sum of squared residuals divided by sample size in the data set you're considering, and then you take the square root.